In this video, we'll discuss experiment 8, where we determine the value of the gas constant R. So we want to set up a reaction that allows us to determine R by knowing the temperature, volume, pressure, and moles of the gas. So the reaction that we're going to be looking at is the decomposition reaction of hydrogen peroxide in water, and it's going to be sped up or catalyzed by the addition of yeast to produce water and oxygen gas. So we'll make sure this equation is balanced by putting the coefficients where we need them. And what we're going to be doing is measuring volume, pressure, temperature, and moles for the oxygen gas, because we know that PUVnert is only an equation that we can use when we're using gases. So in this pre-lab handout, I'm going to go through each of the variables that we're measuring, and I'll also show you where you can look for those on your data sheet as well. So when we're measuring all of these different variables, one that's very easy to measure is the temperature. So we're just going to go ahead and record this value, the room temperature, from the thermometer. In our equation for PV equals nRT, we know that this unit is in Kelvin, so we're going to measure it in degrees Celsius, but write it down in Kelvin. And so when you look at your data sheet, you'll see that there's a space to measure the room temperature in degrees Celsius, which is data that we're actually collecting. And then when we go down to the room temperature part in Kelvin, all we're going to do is take our temperature in degrees Celsius and add 273.15 to get to our Kelvin temperature. Let's go back now to the volume of oxygen gas. So the way this reaction is set up, we have our yeast in this little septum. We have hydrogen peroxide solution that we have measured the volume of, and we know how much we have. And once this tips over, the reaction's going to happen, and we're going to have oxygen being formed in this flask. As the oxygen is formed, it's going to travel through this tube and displace water. So in this Florence flask, oxygen displaces water as it is formed. That water needs to have somewhere to go, so it's going to travel up this tube into the beaker. So we will have water being collected in the beaker here, and we will measure it in a graduated cylinder, a pretty large one so that we know how much we have, and it will measure the volume in milliliters. So in this reaction, the volume of water that is displaced or collected is equal to the volume of oxygen that is formed. So if we go to our data sheet, you'll see that the volume of oxygen evolved is right here. This is going to be measured in milliliters using your graduated cylinder, but when we ask you then to record the volume of oxygen evolved, your unit's going to be in liters. So you take your milliliters, you're going to divide by 1,000, and that will get you 2 liters. Next, we have the pressure of oxygen gas. So generally, what we're thinking about is atmospheric pressure, and this can be measured from a barometer in the lab space. And let's say, for example, that this number, well, actually you don't need a number, so the instructor will tell you what this number is or instruct you to measure what it is when you get to lab. So in here, this flask is just going to have oxygen pressure in it. This beaker is open, so it's going to be equal to atmospheric pressure. And the pressure in the Florence flask is going to have the pressure of oxygen, which will be transferred over, plus some water is going to evaporate naturally because the room is decently warm. So at the end, these two containers should have pretty equal pressures, and we know that atmospheric pressure is equal to the pressure of the oxygen that we form plus the water pressure. So those will all be equalized because of how the experiment is set up. And so if we want to know just the pressure of oxygen, what we'll do is we'll take the atmospheric pressure measured in the room that day and subtract out the pressure of water at the temperature you measured it. So you need to use the table that's in your laboratory manual in order to know, it's on the first page of this experiment, in order to know the pressure of water. So you'll use the table and use the temperature above to locate where on the table you need to write the pressure from. You'll subtract these two values and you'll get your pressure of oxygen in millimeters of mercury, and you will convert that to units of atmospheres so that you can do your calculation of the R value. So if you look at your data sheet, the barometric pressure is the atmospheric pressure from the barometer, and so you'll write that down in millimeters of mercury. We can also find the vapor pressure of water at room temperature from our table. This one will also be in millimeters of mercury. Then when we go down to partial pressure, right here, the calculated data, this is in millimeters of mercury. So this is where you'll take the atmospheric pressure or the barometer pressure and subtract the pressure of water that you got from the table. Okay, so this is from our table in the laboratory manual. And this will give you the pressure of oxygen in millimeters of mercury. Then, one cell down, you're just going to convert your units of millimeters of mercury that you just found to units of atmospheres. Remember that 1 atmosphere is equal to 760 millimeters of mercury. So you can just set up that calculation in that space. Back to our pre-lab handout, we've already done temperature, volume, and pressure, so our last variable that we need to worry about is moles of oxygen gas. So the instructions in the laboratory manual ask you to measure the mass of your setup before shaking, or before the reaction is done. So in here you have your septum containing your yeast, you have your H2O2 solution, and you're going to measure this mass before you do the reaction. You're also going to measure the mass after you do the reaction, because you still have the septum in there, you still have the yeast, and you have what's left in your solution, which is the water, the yeast, the septum. The only thing that changed is that oxygen left. So oxygen left this reaction system. And so if you take your mass before and subtract the mass after, the mass should go down. And the difference in that mass before and after is the mass of oxygen that was generated in that reaction. And if you take the mass of oxygen and you divide it by the molar mass of oxygen, that will give you the moles of oxygen. So if you look at your data sheet, you'll see that you have before and after. And so if you want to find the mass of oxygen, you just take before minus your after. It's a good idea to double check these masses when you write them down, because sometimes people get negative numbers and usually it's because they're transposing some numbers. So make sure you write them down, have your partner double check your work, and if your difference is negative, talk to your instructor. Then you can find the moles of oxygen by taking the mass divided by the molar mass, and that's what you'll write down here. So here your unit will be grams, Here your unit will be moles. And that's pretty much it for determining the value of R. We know that PV is equal to nRT, so if we're just solving for R, you'll take PV over NT with the correct units to solve for the value of R. Make sure that you include the correct units when you do your calculation. You're also going to figure out the percent error. Remember that percent error is your your experimental value, your calculated, minus the accepted. Again, the order of subtraction doesn't matter because we take the absolute value, divided by the accepted, times 100%. The accepted value is given here to you, and make sure you pay attention to your sig figs in this problem. Now let's go through the second handout so that we can figure out this table and find the percentage of hydrogen peroxide by weight. So percent by mass is something that we do when we measure a solution that is obviously a solution, meaning it has some of the solute in a bunch of the solvent. So the peroxide is aqueous, meaning that it's pure peroxide dissolved in a bunch of water. And based on how much oxygen was in there, we can use our balanced equation to figure out how much peroxide was in there to begin with. We know the volume of the peroxide, and we know the mass of the peroxide. We don't actually need the volume for this calculation, but we do need the mass, and we'll be able to find the percent by solution. And interestingly, that you can also compare it to the percentage written on the bottle to make sure that you are correct. So step 1, we're going to use the mass of oxygen to find moles of oxygen, and we can use the moles of oxygen to get the mass of peroxide. So to find the moles of oxygen, we're going to start with our 0.279 grams of oxygen. This is just an example. You would use the number you found. And you actually already converted to moles in your data sheet, so you don't actually have to repeat this step. This is just to make sure that we're all on the same page. So we have this many 0.00872 moles of oxygen that were generated in the reaction that we found by doing the before minus after. Now we're going to find the mass of the H2O2. So we'll start with the moles of oxygen, and we will use our balanced equation to get a ratio. So 2 moles of hydrogen peroxide had to be used up for every 1 mole of oxygen that was formed in the reaction. And we also know the molar mass of hydrogen peroxide is 34.016 grams per mole. From this, we get the mass of our solute, 593 grams of H2O2. So whatever number you calculate, this will be based on your data, you would put in this space. So you can show your work here. That's why we left you some extra space where you converted this step. In step 2, the moles of oxygen to grams of H2O2. We'll also find the mass of solution. So the way that we do that is we take the mass of the flask plus the H2O2 solution, which you measured earlier in the experiment, and we'll subtract just the mass of the flask. So I'm just going to give you some numbers that I've seen in lab. Yours will be different based on which flask you're using, based on how much of your solution you added. You're going to use your numbers here, but I got 18.896 grams of my H2O2 solution. And so this number from step 3 goes here in this space. So this is step 2. And now we can find the percent by weight using this equation. So the percent by weight is equal to the mass of the solute. That's what we found in step 2, divided by the mass of solution that we found in step 3. And we're going to multiply by 100. And in this case, I got 3.14% peroxide solution, which is pretty similar to how it's sold. And so your results from step 4 go in this bottom circle. So that should get you through all of the calculations that you need for experiment 8. Enjoy!